Hi everyone, this is Mrs. GA, and today we are going to review exponents and radicals. So exponential notation, of course, looks like this: a to the power of n, and by definition, a to the power of n equals a times 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 a for n factors. So of course we know that a is called the base and n is called the exponent. And a few special ones to know: by definition, a to the power of 0 or anything to the power of 0 will equal 1. And a to the power of -1 equals 1 over a, meaning if a term has a negative exponent, it flips the term either from the numerator to the denominator or vice versa. Okay, so I want to take a quick second to talk about a really common mistake I see when we're working with exponents. So we have 3 examples here that look really similar. This first one is pretty straightforward. 5 squared, we know, just means 5 times 5, which is 25. But these next two, you'll notice, look really similar. The only difference, of course, is the parentheses. So the way I think about exponents is they only affect the term or number that they are directly touching. So in this case, only 5 is being squared, not the negative. So that means that we actually have a case that looks like this: negative 5 squared. So our answer here is actually negative 25. So remember, in this case, the negative is not being squared, only the 5. Now here, since our negative is explicitly grouped with our 5 with the parentheses, that means that we're squaring both the 5 and the negative. So essentially we're doing -5 times itself. And we know that a negative times a negative becomes a positive. So in this case, it's positive 25. So you see that something as small as a set of parentheses can actually completely change your answer. So just be careful when you have a negative and you're working with exponents. Okay, so we're going to do a quick review of our laws of exponents. First, multiplying two terms with the same base that have exponents, our rule is to add the exponents. So a to the power of m times a to the power of n is a to the power of m plus n. Just add up the exponents. How do you divide when you have the same base and exponents? You subtract the exponents. So we have a to the power of m minus n. Raising an exponent to another exponent, our rule is to multiply the two exponents. So it's a to the power of m times n. If you are raising a product to a power, we actually will raise both numbers or terms to that exponent. So a times b to the power of n is a to the power of n times b to the power of n. Both terms are raised to that power. If you are raising a quotient to a power, same idea. Both parts of your quotient are raised to that power. So you have a to the power of n divided by b to the power of n. And here, what happens if you have a negative exponent? Remember, negative exponents they flip terms either from the numerator to the denominator or vice versa. So here, since both of these terms are being raised to the negative exponent, both a and b will flip. So this actually becomes b over a to the power of n, which of course we could simplify it as b to the power of n over a to the power of n, or we can leave it like this. And lastly, here we have two separate negative exponents. So the exponents are going to travel with the term when you flip them. So a to the power of n will flip to the bottom. And notice that the n travels with a. And b to the power of m will flip to the top. And notice that m stays with b. So we're going to be using these different laws to help us simplify different expressions. All right, let's try one example together. So when you are simplifying expressions with exponents, there's a lot of different ways you can approach it. So I'm going to start just by looking at this first part here. And we're going to use one of our properties, which was raising a product to a power. So remember, each term gets raised to that power, and when we're raising a power to a power, we multiply the exponent. So here, 2 cubed is 8, and x to the 5th cubed, well, 5 times 3 is 15, so we have x to the power of 15. And here, 3 times 3 is 9. All right, so in this next part, I'm going to combine two of our properties into one. We're going to address the negative, and we're going to raise all of these terms to the power of 2. So the first thing that's going to happen is the negative is going to flip the numerator and denominator. So we have x to the power of 4 over y, and then x to the power of 12 over y to the power of negative 3. And then when we do that, our negative simply disappears. So it's still squared, but the negative is no longer there. So let's keep working with this side for another step. So now we're going to make sure that each term is raised to the power of 2. So this is going to stay the same for now. And this becomes x to the power of 8, y squared, over x to the power of 24, y to the power of negative 6. So again, I'm going to multiply all of my exponents by 2. So at this point, there's a few different things we can do. We could use our quotient law first and subtract our exponents here, or we can use our product law first and we can multiply the numbers that are in our numerator. So let's do that. So here I'm going to be multiplying this with our numerator. So we will have 8. And remember, our rule for multiplying with exponents is to add the exponents. So then we have x to the power of 23, y to the power of 11, and then all over x to the power of 24, y to the power of negative 6. Now we're going to use our quotient property, and remember, when we're dividing with exponents, we subtract them. So 8 is just 8. Here we have 23 minus 24, so that gives us x to the power of negative 1. And here, just be careful, we actually have 11 minus negative 6. So remember, when you're subtracting a negative, you're actually adding. So we have y to the power of 17. And our last step is going to be to address this negative exponent. We typically don't leave a negative exponent in our final answer. So here's one thing that I really want you to be careful with. When you have a negative exponent, only that term is flipped. So this 8 does not have a negative exponent. It's going to remain in the numerator. Y does not have a negative exponent. It's going to remain in the numerator. So only x will be moved to the denominator. So our final answer here will be 8y to the 17th over x to the first power. And this is our final answer. Now again, there's a number of different ways you could have approached this problem. As long as you end up with the same answer, that means that you used your loss property and you're good to go. Okay, at this point, I'm going to ask you to pause this video and give this problem a try. We will check your answer in just a few seconds. Okay, so the answer should be a to the power of 6b cubed. So here's one way that you can get to that conclusion. Of course, the steps that you took might be in a little bit of a different order than what you did or than what I did, but as long as you end up with this answer, you should be fine. So I used my power property first, and I multiplied my exponents in the numerator, and then I combined the terms in my numerator by adding the exponents. And last, I subtracted my exponents to get a to the 6b cubed. Okay, so now we're going to do a quick review of radicals. So we know that, of course, a radical is any type of root. So here we know that square root of a equals b means that b squared equals a. So, of course, we know that square root of 4 equals 2 because 2 squared equals 4. So if you have a square root, it's you're looking for something squared. And that means that if you have the nth root of a equals b, that means that b to the power of n equals a. So for example, with real world numbers. We know that the cube root of 8 equals 2 because 2 cubed is 8. Now, of course, if n is even, if you're taking an even root, we know that a and b must both be positive. So that means that you cannot take an even root of a negative number. It's not possible to do. And if you're taking an even root, your answer will always be positive. So we're going to talk about, we're going to review some of the properties of nth roots. So the nth root of a times b can actually be split up to the nth root of a times the nth root of b, and vice versa. If you have a common index, which is your root, and you have two separate radicals, you can multiply the insides of your radicals, which is called the radicand, to get this result. So here, the nth root of a over b, of course, can be rewritten as nth root of a divided by nth root of b. So these can be useful when you're simplifying. Like sometimes it's easier to simplify the numerator and denominator individually rather than dividing first, then simplifying. Here, if you have the mth root of the nth root of a, your indexes can actually just be multiplied. So it's the nth root of a. Here, if you have an odd n value, the nth root of a to the n is just going to be a. So like if you have the square root of a, or the cube root of a cubed, it's just going to be a. And another way of thinking about it is if the exponent and the index are the same, they kind of cancel each other out. And however, if you have an even n value, for example, the square root of a squared, your answer is actually the absolute value of a. The reason for that, we're going to do an example in just a moment, is we don't know what a is. A could be a positive value, a could be a negative value. So if you're left with a variable, you need to make sure that our answer is positive. And the only way to do that is by adding the absolute value signs. But of course, this is only something you need to worry about with even roots, because odd roots, it's okay if you are negative. Okay, so here we're going to try an example together. We're going to simplify 4th root of 81 x to the 12th, y to the 4th, z to the 8th. So just a really quick review of simplifying radicals. And this is probably something you already know. If I'm simplifying something like the 4th root of 81, I'm looking for a factor that can be raised to the power of 4. So one way you can do this is really old school, but you can just do a factor tree. So we know that 81 is 9 times 9, and you can factor it all the way down to the prime factors. And since it's a 4th root, again, we're looking for a group of 4. So here's my group of 4. So 4th root of 81 is just 3. So again, we're trying to look for groups that match the index or whatever the nth root. So we have 3. Here, I know that with x to the power of 12, there's 3 groups of 4, so it's going to be x cubed. Here, when I have y to the 4th, that's 1 group of 4, so it actually just becomes y. And then 4th root of z to the 8th is just z squared. So again, I can kind of say, okay, 4 goes into 12 3 times, 4 goes into 4 1 time, but 4 goes into 4 goes into 8 twice. So now there's one more step. This answer isn't actually technically complete. So that property we just talked about, when you have an even root, we need to make sure that our answer is definitely positive. So 3 is just 3. 3 is positive 3. There's no question about that. However, x cubed, we don't know if this value is positive or negative because, well, we don't know what x is. So the only way we can make sure that this is, in fact, a positive value is by actually writing it like this. Absolute value of x times x squared. So I can leave x squared because any number squared will be positive. But then I have to have this absolute value of x right here. Same goes for the y. Y is a variable. I don't know what y is. The only way to ensure that my answer is positive is by writing it with an absolute value sign. And this last term, z squared, Well, since this number is being squared, I know that the result will always be positive, so I can actually leave it as z squared. So I know this seems a little bit ticky-tacky, and it is a little bit nuanced, but you do need to make sure that your final answer, when you have an even root, is positive. Okay, go ahead and pause the video again and give this next example a try. Okay, let's check your work. So the fourth root of 625 is 5. So either you can use your calculator to find that, or you can do a factor tree. 4 goes into 8 twice, so p squared. And of course, regardless of whether p is positive or negative, since we're squaring it, the result is positive. So it's okay to leave p squared. 4 goes into 4 once, so fourth root of q to the fourth is q. However, again, we need to make sure that our result is a positive answer, so I need to throw those absolute value signs around q. Okay, now we're going to do a quick review on how to add or subtract radicals. You just need to be careful not to fall into a really simple mistake that people will make typically if they're rushing. I want to remind you that square root of 5 plus square root of 5 is not equal to the square root of 10. You can't just add the radicands when you're adding radicals. So remember, the way we add or subtract radicals is first by simplifying. You need to make sure your terms are simplified completely. And then you combine only radicals that have the same radicand, which is the inside of your square root or whatever root. And the way you do it is by adding the coefficients, essentially. Here, think of this as 1 root 5 plus 1 root 5, which gives us 2 root 5. So you kind of add it the same way that you would add variables. X plus x is 2x. Root 5 plus root 5 is 2 root 5. All right, let's try one example together. So we're going to start with the first step, which we just talked about, which would be to simplify all three of these radical expressions before we combine them. So let's start with cube root of 24. I can rewrite it as cube root of 8 times 3. We know that the cube root of 8 is 2, so it becomes 2 times the cube root of 3. That's the simplified form. Let's do 81. So we can rewrite this as the cube root of 27 times 3. If you know your perfect cubes, it makes your life a lot easier. Cube root of 27 is 3, so this becomes 3 times the cube root of 3. And we can rewrite this guy as the cube root of 8 times 2. Cube root of 8 again is 2. So here we have 2 times the cube root of 2. So now we can add our radicals that have common radicands. You might notice that these are both cube root of 3. And this guy is the cube root of 2, which means that I can combine these two, and this guy is going to be on his own. So here I have 2 cube root of 3, and I have 3 cube root of 3, so if I combine those, I have 5 total. 5 cube root of 3, and again, sometimes you just can't combine two terms, so our final answer actually looks like this. So, don't oversimplify, don't combine when you can't. Sometimes you will end up with multiple radicals in your answer. Okay, go ahead and pause the video real quick and give this example a try. Okay, let's go ahead and check our answers here. So to simplify square root of 25, you can think of it as square root of 25 times 5. Know your perfect squares. Square root of 25 is 5, so you get 5 root 5. Square root of 245, if you do a little factor tree, you quickly get 5 times 49. Hopefully you recognize that as a perfect square. And so since I have a common radicand, I can add the coefficients. 5 plus 7 is 12. Okay, the last thing we're going to review is rational exponents. So hopefully you remember that rational exponents is just a different way of writing a radical and vice versa. So if you have a to the power of m over n, rational again is just like a fancy word for a fraction. We can actually rewrite this as nth root of a to the power of m. So I always say inside out, so the inside and then out. And we can go the exact opposite as well. Nth root of a to the power of m. Remember, it goes inside out. We can rewrite that as a to the power of m over n. So it can be really useful to rewrite a radical expression as a rational exponent when we're simplifying. So it's really good to be able to go between the two really easily. And if you ever get stuck, my advice to you is to just see if there's some way you can rewrite it, and sometimes that will open doors. So let's try this last example together. So here we have 2 times the square root of x times 3 times the cube root of x. So of course we can multiply 2 and 3. That's no big deal. We can say 6, and then we have the square root of x, and then we have the cube root of x. So here, the way it's written, we actually can't combine or multiply these two radicals. You can't multiply a square root with a cube root. So instead of just saying, okay, I guess we're stuck, there's nothing more we can do, I'm going to try to rewrite these expressions. So I'm going to rewrite square root of x as x to the power of 1/2. So remember, this is just x to the power of 1, and when it's a square root, it's implied that the index is 2. So if I do inside out, it's 1 over 2. Here, same thing, we can add a 1 in here. Let's rewrite this as x to the power of 1/3. So now, since I have a common base, I can actually multiply these two terms. I can do 6 times x to the power of 1/2 plus 1/3. And you can always go on the side and add up those fractions. 3/6 plus 2/6 is 5/6. So our final answer is 6x to the power of 5/6. And we can leave it like this, or we can rewrite our x term as a radical. We can say 6 times the 6th root of x to the 5th. Either way is fine. So just remember, sometimes when you're working with radicals, it can be helpful to rewrite them with a rational exponent to see if there's more that you can do to simplify. Okay, here's your last U-try. Again, pause the video and give it a try on your own. And again, my hint to you is try rewriting your radicals with rational exponents. Okay, let's check our work. So here you can see that I turned the entire radical into exponent 1/2, and then within my radical I turned this guy into x to the power of 1/2, and then I multiplied these two terms by adding my exponents. 1 plus 1/2 is 3/2, and then remember the rule for raising an exponent to an exponent is to multiply. 3/2 times 1/2 is 3/4. So you can leave it like this, or you can say the 4th root of x cubed. Okay, that is all for this video. Thank you so much for watching.